in the last lecture we have discussed the limits concept. So, here in this lecture we will prove few results related to the limits of the sequences and functions, and then finally we will discuss the Bolzano-Weierstrass theorem for some results on limits of sequences of real numbers. Few more results on this. The first result which we quoted is a theorem. The theorem 1 says if xn is a convergence sequence, of real numbers, and if all the terms of the sequence xn are positive, non-negative, greater than or equal to 0 for all n belongs to capital N. If all the terms of the sequence are non-negative, then the limit cannot be negative. Then the limit of this x, which is the limit of xn over n, will also be greater than or equal to 0. It cannot be a negative limit. The limit of the sequence of non-negative term will always be a non-negative. The proof of this is, let us prove by contradiction. Suppose the limit is negative and then apply the condition for this. So, let us suppose limit x is negative, say x is equal to minus epsilon. Okay. Then for this epsilon, which is greater than 0, there exists a positive integer, say k depends on epsilon, such that mod of xn minus xn, because this sequence is a convergence sequence. So, basically the xn will lie between the two terms xn minus x remain less than epsilon. That is, the xn will lie between these two terms, less than x plus epsilon and greater than x minus epsilon for all n greater than k. Is it not? Now, epsilon is already chosen minus x. So, from here this shows that xn is less than minus x plus x minus x, that is 0, and this is true for all n greater than k. It means the large number of the terms xn are negative. This shows that sequence xn has large number of terms, negative terms, which contradicts. Why contradicts? Because xn already are positive, therefore our assumption is wrong. So, x must be positive. That's answer. Then another results, two says if xn n by n are two convergence sequences, of real numbers, and if xn is less than or equal to yn for all n belongs to capital N natural number, then the limit will also follow the same inequality. Limit of this is also less than or equal to limit of yn. And similarly for the sandwich theorem, which we have shown earlier, that if xn and by n are the two sequences and Zn is a sequence which lies between xn by n, and if the limit of xn by n converges to the same limit, then Zn will also. So that is the sandwich theorem, which also we have shown earlier. Okay. So this is what now next is result is divergence sequence we have discussed. Now theorem third, let the sequence xn converges to x, then the sequence mod of xn, this sequence of absolute values converges to mod x. That is, if the limit of the sequence is x, then limit of the mod xn will also be mod of x. The proof is very simple. This follows from this inequality, xn minus x is greater than equal to mod xn minus mod x, triangular inequality. We know this result. So if xn converges to x, means for a given epsilon greater than 0, there exists an positive integer k such that for all n greater than equal to k, we have this part is less than epsilon. So this part less than epsilon means this part. So this shows the limit of mod xn over n is mod x. So that's what is so okay. Then if xn be a sequence of real numbers, a sequence of real numbers that converges to say x, and suppose that xn is greater than equal to 0, then the sequence under root of xn, this sequence of positive square root converges to under root x. Okay. The proof is, since xn is a sequence of real number that converges to 0, and we are assuming xn to be greater than 0, so limit point cannot be negative. So we are considering only two cases, when this is x is equal to 0 and x is greater than 0. So case 1, when x is equal to 0. So when x is equal to 0, xn sequence converging to 0, that is xn is tending to 0, where xn's are all positive, greater than or equal to 0. Okay, they are 0. So for a given epsilon, so by epsilon, for given epsilon greater than 0, there exists an k in positive integer k such that xn which is greater than equal to 0 will less than xn minus 0 is less than, say, epsilon square for all n greater than k. Therefore, under root of xn will less than epsilon for all n greater than k. So the limit of the sequence xn will, so limit of the xn when n tends to the under root of this will go to 0. Similarly, if we take x to be non-zero, then in that case non-zero and greater than 0, because x greater than 0, then we consider under root xn minus under root x. Now next rationalize it. So multiply and divide by under root xn plus a, we get xn minus x over root of xn plus root x. Okay. Now this is given under root of xn and both are positive. So this will be less than equal to, so if I take mod of this, then this is less than equal to mod xn minus x, and so this part under root xn plus x is greater than 0. So this will be greater than equal to root x. So it will be less than equal to root x. This is positive, this is positive. So this will be greater than root x. So 1 upon this will be less than. Therefore, this limit of this is the same as the limit of this under root x, but this limit is tending to 0. So this implies that limit will go to the, so this implies limit of under root xn over n is under root x. So nothing, not much to be proved. Okay. Then we go for monotonic sequence. We have discussed it already. Now, yes, subsequences, that part is left. So let us see concept of the subsequence. Subsequences of a real number, of real numbers, real sequence. Okay. So let xn be a sequence of V, a sequence of real numbers and let n1 less than n2 and so on be less nk be strictly increasing sequence of natural numbers then the sequence x and k, then this sequence x and k given by x and 1, x and 2, x and k and so on. This given by this is called a subsequence of x. Subsequence of xn. Subsequence of xn. Okay. For example, if we take this say sequence xn is 1, 1 by 2, 1 by 3, 1 by 4 and so on. This is a sequence xn. Now if we take the sequence half, 1 by 4, 1 by 16, 1 by 8, 1 by 16 and so on, then this is a subsequence, because this is the second point of this. So this is the second term, this is the fourth term, this is the 8th term, is it not? And like this. So we are getting a n1, n2, n1 is less than n2, less than n3 and so on, we are seeking. But if we take a sequence like this, say 1/4, 1, then let it be 1/8, then 1/6 and so on, then this is not a sequence, not a subsequence. Why? Why it's not a subsequence? It's a sequence, but it's not a subsequence. Why? Because the order is not retained. Because here n1, this is the fourth term, this is the first term, this is the first term, this is the 8th term, this is the 6th term. So there is no such order like this, n1 less than n2 less than n1 is not less than n2, n2 is less than n3, but n3 is not less than n4, like this. So it does not satisfy the criteria of the subsequence, like this. Please check, is it okay? So that will be the now this is very interesting results here. The result said, okay, monotone subsequence theorem, monotone subsequence theorem. The theorem says if x equal to xn is a sequence of real numbers, then there is a subsequence of x that is monotone. So this is a very interesting result, that every sequence has a monotone subsequence. Every sequence, that is, the result is very interesting, that every sequence has a monotone subsequence. So that's the proof. Let us see, suppose we have a, first we define the term, say x1, x2, xn. Let us define this term, which we call it the as a peak. Okay. The mth term xm is a peak. The mth term xm in the sequence xn is a peak. If xm is greater than equal to xn for all n such that n is greater than equal to n. Means like this, if suppose we are having a sequence x1, x2, xn and so on, and if we identify some term xm here such that after this all the terms of the sequence are of decreasing nature, and above it is bounded by xm. This term x1, x2, xn may behave appropriately. Maybe x1 is greater than x2, x2 may be less than x3 and so on, we do not care. But if we find out some m such that xm is greater than after a certain stage all the terms of the sequence, then we say the peak xm is the peak of the sequence xn. Okay. So what we should do here, that every sequence, using this concept we will prove that every sequence will have a monotone subsequence. So let us see the two cases when the sequence has an infinite number of peaks and the case when the sequence have only finite number of them. So suppose sequence x has infinite number of peaks. Let them arrange this thing. Arrange these peaks. Suppose the peak is xm1. Okay, where then xm1 is greater than equal to xm2, greater than and so on, because m1, m2, m3 these are the terms. M1 is less than M2, less than M3, but the peak M1 is the peak. After this all the terms of the sequence are less than it. Then xm2 is another term such that after this all the terms are less than this, and like this. So arrange this. So this sequence will have a decreasing. So, the sequence of the peaks, this sequence of peaks is a decreasing subsequence, is a decreasing subsequence, of x. So, in case of the infinite, what we identify the points, first peak which is such that after this all the terms of the sequence are less than this, identify x1. Then after certain stage again you will find out some term for which the condition that xm is greater than xn satisfy for all n greater than m, and like this. So, arrange this thing. So, you will get a monotonic decreasing sequence for that. Now, if x has a finite number of, if x has a finite number of peaks, maybe 0 also, maybe 0, no peak, this is also possible. So, if the finite number of 0, let these peaks be in increasing, this will listed by increasing order. Okay. So, let this peak be arranged in increasing order. Let us say in increasing subscripts. That is, if m1 is less than m2, that xm1, xm2, these are the peaks, xm say r, and arrange in the increasing circuit, that is m1 is less than m2, less than m3, and this is mr, arrange in this. Now, let us pick up this term, let pick up the sum, let S1 is the term which is after this peak or MR peak in this first index beyond this. Then this S1 cannot be a peak because this is the peak and this is the last peak. So, we cannot take any number which is greater than this can be a peak. So, S1 is not a peak. Okay, means x is finite, then S1 be first index. Okay. Once S1 is not a peak, it means there will be some point, here is MR. So, S1 is this point something. Now, S1 is not a peak, it means there may be some number S2 which is greater than S1, then only it is a S2 we can identify. So, there exists an S2 such that S2 is greater than S1 because S1 is not a peak. So, once it is greater than, then the corresponding sequence x S1, obviously this peak is less than x S2. This term will be less than this, okay, corresponding. Again, since x is 2 is not a peak, so we can, there exists another term S3 greater than S2 such that the term of the sequence XS2 is less than XS3 because this is not a peak, this is not a peak. So, a term will be there which is greater than this and continue this. So, once you continue, then we get a sequence X, X, S, K, a sequence, increasing sequence of X which is monotone increasing sequence. So, this shows that every sequence will have a monotone subsequence. It has a subsequence of X that is monotone. Following these two, we have an important result which is known as the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem. What this theorem says, a bounded sequence of real numbers has a convergent subsequence, has a convergent subsequence, has a convergence. So that's very important result, because it shows that every bounded sequence of real, it may not be a convergence, like -1 to the power is not a convergence, but it has a bounded convergence subsequence. At least one bounded convergence subsequence will be there. The proof is based on the previous result. Suppose xn is a bounded sequence, is a bounded sequence of real numbers, of bounded sequence of real number. Then it has a subsequence xn that is monotone. Now, since it is a bounded sequence of real number, so it will have, then it has, suppose a bounded sequence of real number, okay. Then it has a subsequence, because every sequence has a subsequence, it had a subsequence x and k, that is monotone by the previous result, that is monotone by the previous result, okay. Now, since subsequence is also bounded, since this subsequence is also bounded, so it follows from the every, now one thing, this is a subsequence which is monotone and is bounded. So, bounded by the monotone theorem, monotone convergence theorem says that if a sequence which is monotone and bounded above or below must be convergent. By monotone convergence theorem, this sequence will be convergent. So, this proves that a bounded sequence of real number has a convergent subsequence. That proves the result. Now, this completes your first module, that is Cantor's third, Dedekind's and theory of sequences. Now, here the books which I followed, books which are used, reference, the first book which I taken as a introductory by Robert G. Bartle, introduction to real analysis. Second book which I followed is by Enschler, that is theory of real variables. I think that is the theory of real variables or something. I will give the name exactly, theory of real variables or theory of real functions, like that. So, mainly these two books I followed for this section. Thank you very much.